In this video, we will talk about solutions and how to resolve the problems. All the topics about this video will be listed below the video in YouTube with links to the different parts. The first part is going to be a review of the metric system, then calculations involving solutions, then dilution calculations, and the last one is going to be mixing two solutions of different concentrations. Sometimes the volume in your problem is given in centimeters cube. Sometimes they give your volume in milliliters. Sometimes they use liters, or sometimes they use decimeters cube. Some students get very confused about this, so let's talk a little bit about this topic. If we have this small cube, the one that you have here in the corner, and we pretend that this one has 1 centimeter in each side, and we calculate the volume of that small cube, the volume is going to be equals to 1 centimeter cube. That is the volume B that I calculated in green, okay, the small volume. So 1 centimeter cube, the relationship with milliliters is that if you take a cube of 1 centimeter in each side, so the volume is going to be 1 centimeter cube, and you fill it up with water, is going to hold exactly 1 milliliter of water. So in other words, when they give you centimeters cube or milliliters, it's exactly the same thing numerically. 1 centimeter cube is equals to 1 milliliter in terms of the numbers that I can use in my problems. Now what I'm going to do is to calculate the volume of the big cube. The big cube has, if you count them, is 10 centimeters. Here I have 10 centimeters, and here I have 10 centimeters. Okay, so up to the end. So if I calculate the volume in violet now, the big cube is going to be 10 centimeters times 10 centimeters times 10 centimeters. That is going to be 1,000 centimeters cube. That means that this one is going to hold 1,000 milliliters of water, because each centimeter cube holds 1 milliliter. So I can say this equivalence to. Now, if you look at the value, and I'm going to use another color so you know exactly what I'm doing. 10 centimeters is the same as 1 decimeter. So the big cube has 1 decimeter in each side. Pardon, I'm sorry, it doesn't have a 3 here. So it's 1 decimeter. So if I calculate the volume red, which is the same as the violet, it's going to be 1 decimeter times 1 decimeter times 1 decimeter is equals to 1 decimeter cube. But the volumes here, the volume in violet and the volume in red, they are the same. That means that I can say that 1 decimeter cube is equivalent to 1,000 centimeters cube, or they are equivalent to 1,000 milliliters, which of course they are the same as 1 liter. That's what we are going to use in our problems all the time. So you need to remember that milliliters are equivalent with centimeters cube, and decimeters cube are equivalent with liters. Now we are going to begin with the problems about solution. Before getting to the actual problems, we are going to see how to prepare solutions from solids. So the first step will be calculating, of course, the amount of solid that we need to prepare the solution. We measure that with if we have a digital balance, is better. Then we dissolve the solute in some distilled water. You have to be careful that it's not more than half of the content volume that we are going to prepare, so we don't overpass that. After we dissolve the solid, we pass it through a funnel inside the volumetric flask. we wash the contents inside the volumetric flask. So we know that every ion that is present of the solute in the beaker is going to be washed inside the volumetric flask. And then we adjust the volume with the drop-in pipette or with the washing bottle. Remember to use distilled water all the time. Once we get to the mark, we are going to tap it, and we will move it several times till it mixes thoroughly, and the solution concentration will be evenly distributed throughout the liquid. In these following examples, we are going to calculate molarity, which is going to be the only expression of concentration that we are going to cover in this video. In this first example, we need to calculate the molarity of a solution that contains 0.200 moles of sodium chloride in 0.5 decimeters cube of a solution. So the molarity is equals to the number of moles divided by the volume in decimeter cube of liters. So the only thing that we have to do is 0.200 divided by 0.500. This is going to be the same as 0.4 molar of sodium chloride. In this second example, the molarity has to be calculated too. And we have the number of moles of solute, that is 0.500 moles of copper chloride, copper 2 chloride, and the volume is 250 centimeters cube. We need to transform this volume into decimeters cube or liters. I know that 1000 centimeters cube is equals to 1 decimeter cube. So this is going to be the same as 0.250 decimeters cube. And now I can apply the formula. The number of moles is 0.500 divided by 0.250 decimeters cube. This is the same as 2 molar, or with the correct amount of significant digits, 2.00 molar of copper chloride. In this third example, they don't give me the number of moles. They gave us the 0.45 grams of sodium nitrate. So you need to calculate the molar mass of sodium nitrate. And that is going to be 23 for sodium plus 14 plus nitrogen plus oxygen, which is 16 times 3 because it appears 3 times. That is 85 grams of sodium nitrate per mole. So for the molarity, we have the one that we need to calculate. The number of moles, we don't have it, but we know that we have 0.45 grams of sodium nitrate, and we need to pass that into moles. So 1 mole is equals to 85 grams of sodium nitrate. That is the same as 5.29 times 10 to the negative 3 moles. And then the volume is also given in milliliters. So the volume is 265 milliliters, and we divide that into 1000 to get into liters, 0.265 liters. And now I can apply the formula. The molarity is equals to 5.29 times 10 to the negative 3 moles divided by 0.265 liters. And that is the same as 0.01996 molar, but with the correct amount of significant digits that are 3 all the way. So this is going to be 0.0200 molar of sodium nitrate. In the examples that we did before, we calculated molarity. Now we are going to calculate the amount of solute. Sometimes they ask you the number of moles. Sometimes they ask you the mass of the solute that is present. So we are going to see which are the examples. In this first example, we need to calculate the number of moles of potassium hydroxide. They give us the relative molecular mass for that are present in 25 milliliters of a solution. So let's pretend that I have a container that has a solution that we know that is 0.050 molar, and we extract 25 milliliters. And we need to know how many moles of solute are present there. Okay, that is what they are asking. So we know that the molarity is 0.050 moles per liter. The volume is 25 milliliters. I know that 1000 milliliters is equals to 1 liter. So this one is going to be 0.025 liters. And the number of moles is what we need to calculate. The number of moles is equals to the volume times the concentration, or molarity. So the volume is 0.025 liters, times the molarity, that is 0.050 moles per liter. Liters go with liters, and the number of moles is equals to 1.25 times 10 to the negative 3 moles of potassium hydroxide. That means that in my 25 milliliters, I have 1.25 times 10 to the negative 3 moles of the solute present. In this example, we need to prepare 125 milliliters of a solution 1.5 molar. So with these two values, we are going to calculate the number of moles of solute, and then in the second step, we will calculate the grams of potassium chloride. This is going to be step 1. This is going to be step 2. So in step 1, we calculate the number of moles, which is the volume times the concentration. Remember that the volume has to be in liters or decimeters cubed, so I'm going to automatically divide by 1000 so I don't forget. So the number of moles is equals to 0.125 liters times 1.5 moles per liter. Liter goes with liters, and the number of moles will be 0.1875 moles of potassium chloride. In the step 2, we need to take this amount of moles and pass that into mass. So I have 0.1875 moles, and I know that 1 mole of potassium chloride is 74.5 grams of potassium chloride. This one cancel with this one, and the answer will be 13.97 grams of potassium chloride. If I express that with the correct amount of significant digits, this one has 2, so I should say around 14 grams of potassium chloride. In the next examples, we are going to calculate the volume of a solution that contains a certain number of moles or a desired number of grams for solute. In this particular case, we need to calculate the volume of a solution that will contain this amount of moles of hydrochloric acid, and the concentration of the solution is 0.01 molar. We need to know how much volume will be containing 5 times 10 to the negative 3 moles of the, in this case, hydrochloric acid. So we know that the number of moles is equals to volume times the molarity, and dividing in both sides by molarity, we can calculate the volume. Be careful, because this is going to be in liters or decimeters cube. After that, we need to calculate the volume in centimeters cube. So the volume is equals to the number of moles, which is 5 times 10 to the negative 3 moles, divided by the molarity, which is 0.01 moles per liter. Okay, so moles go with moles, and the volume would be equals to 0.5 liters, or we can put that as 500 centimeters cube or milliliters. In the case that I need to calculate the milliliters, but they give me the mass, the first step would be calculating the number of moles here. So I have 22.2 grams of calcium chloride, and I will pass this into moles. 1 mole of calcium chloride is equals to 111 grams of calcium chloride. Grams go with grams, and this is going to be 0.2 moles of calcium chloride. This is the first step, which be calculating the number of moles. The second step would be calculating the volume. So we know that always the number of moles is equals to the volume times the concentration, which is the molarity. The volume is what we need to calculate. So the volume is going to be the same as the number of moles divided by the molarity. So volume is the number of moles, 0.2 moles, divided by the molarity, which in this case is 0.05 moles per liter. It's very important that you put the units so you remember that the volume that you are going to obtain is in liters, and that is 4.00 liters, but they asked me in milliliters, so it's going to be 4,000 milliliters. Or if you want to express that into 3 significant digits like this one, I would put 4.00, 3 significant digits, times 10 to the third milliliters or centimeters cube. The next problems are about dilution. Dilution is a process that we use a concentrated solution to form what we call a dilute solution. So in here you can see that we have a solution that is darker than this one. That is because I will extract a certain amount of liquid of that solution, and I will add water until the mark again to form a new solution. So we're going to see which is the information that we can extract from there. It's very important that you need to know that I can calculate the number of moles that I am extracting. If I calculate the number of moles here, the number of moles is equals to the volume of the concentrated solution times the molarity of the concentrated solution, and this is going to be the number of moles of the concentrated solution. The volume that I extracted is this one here, okay? So in this case, it's going to be the extracted volume. Then I add water, and here I'm going to have also I can calculate the number of moles for the dilute solution. So the number of moles of the dilute solution is equals to the volume of the dilute solution times the concentration of the dilute solution. Now, the volume of the dilute solution depends on which is the volumetric flask that I'm using to prepare the solution. So this is the volume that I prepared, okay? Now, very important thing, and pay attention to this. If you know that the number of moles here is the one that I extracted, and the only thing that I added was distilled water, the number of moles of the dilute solution have to be the same. Now, if we know that from math, we know that whenever something on the left side of two equations is the same, the right side of the equation also will be the same. That means that the volume times the concentration of the concentrated solution have to be the same as the volume and the concentration of the dilute solution. So in this case, I can write the volume of the concentrated solution times the molarity of the concentrated solution is equals to the volume of the dilute solution times the molarity of the diluted solution. Now, in the particular case that I'm doing, for example, I'm preparing a solution for you in the lab, and I use sulfuric acid. Sulfuric acid comes in a concentrated solution of 18 molar, okay? And let's pretend that I use this volumetric pipette that you can see here that has a 25. That means that I extracted 25 centimeters cube. So the volume of the concentrated solution and the molarity of the concentrated solution are known. Why? The volume of the concentrated solution is the volume that I extracted, 25 centimeters cube, and the molarity of the concentrated solution is 18 molar. Now, let's pretend that I use here a 250 volumetric flask, 250 centimeters cube volumetric flask. The volume of the dilute solution is going to be 250 centimeters cube. And the concentration, or the molarity, let's put molarity here so you understand. The molarity of the dilute solution is going to be the same as the one that we are going to calculate. How do we calculate that? By using this formula here, okay? So in this case, instead of putting C and D, I can put solution 1 and solution 2. So in general, if you go to the to any book or anything, you may find this equation as volume 1 concentration 1 is equals to volume 2 concentration 2. Volume 1 is the concentrated one, volume 2 is the diluted one. It's very important that you organize your data here, because if you don't organize your data, you may flip the volumes or the concentrations and everything is going to be wrong. So in this case, the volume 1 is 25 centimeters cube times the concentration, which is 18 molar. That is going to be equals to 250 centimeters cube times the molarity of the concentration of the molarity of the new solution. That is what I want to calculate. I'm sorry. So remember that when we calculate the number of moles, I always made emphasis in the volume that has to be in decimeters cube or liters. In this case, if we pass these to decimeters cube or liters, I'm going to be divided by 1000. Yes, so I transform this one in decimeters cube. The same thing here. I put 1000 and I put this one in decimeters cube. But the problem is that the 1000s cancel, so it really doesn't matter if you work in centimeters cube or decimeter cubes when you are talking about dilutions, unless you are calculating the volumes. You are going to obtain the volumes in the same unit that you used. My advice, work in decimeters cube all the time, and the worst case scenario, you are going to cancel the units, and the 250 can be canceled because it's 10 times 25, so 18 divided by 10 molar is going to be the molarity of the, or the concentration of the solution 2. So in this case, the molarity is going to be 1.8 molar, which makes sense because we are diluting the 25 into 250. If the volume increases 10 times, the molarity should decrease 10 times as well. In this example, we need to read very carefully all the prompts that we received, just in case. We have 20 milliliters of a solution of potassium permanganate 0.025 molar. We transfer the volume into a volumetric flask. That means that this one here is the concentrated solution. So this is 0.0125 molar, and we extract 20 centimeters cube, and we put that into a volumetric flask, and we add water until we have 250 centimeters cube. 250 centimeters cube. So volume 1, concentration 1, volume 2, and concentration 2. It's very important that you organize your data. I don't know how many times I said that already. So the volume 1 is 20 centimeters cube. The concentration 1 is 0.0125 molar. The volume 2 is 250 centimeters cube, and the concentration 2 is what we need to calculate. So if we need to calculate the concentration 2, is equals to volume 1 times concentration 1 divided by the volume 2, because it was multiplying here, no? So the concentration 2 is 20 centimeters cube times 0.0125 molar divided by 250 centimeters cube. Centimeters cube, go with centimeters cube. The 0 goes with the 0, and the concentration 2 is equals to 1. I have two significant digits here, so I can put 1.0 because it's 1 exactly. So 1.0, two significant digits, times 10 to the negative 3 molar. After you finish, you should check if the numbers make sense. This is around a little bit more of 10 times smaller the concentration than the original one, and we diluted more than 10 times, so that makes more or less sense. This example is something that I do very often in the lab, because the hydrochloric acid comes in jars that have a concentration of 12 molar. And let's say that I need to prepare 250 centimeters cube of a solution that is 2 molar. Okay, so I need to know how much volume would be necessary to form 250 centimeters cube of a 2 molar solution. So the same as always, we need to organize the information. Volume 1, concentration 1, volume 2, concentration 2. That is very important. So in this case, it says we need to prepare 250 centimeters cube of a solution 2 molar. That is the volume and the concentration of the diluted solution. So the volume is 250 centimeters cube and the concentration is 2.00 molar. And the concentration 1 is 12.0 molar. That is the stock solution. And the volume 1 is what we need to extract. We need to figure out which is going to be the volume that we need to extract. So volume 1 is equals to concentration 2, I'm sorry, times volume 2 divided by concentration 1. Volume 1 is equals to the concentration 2, which is 2 molar, times 250 centimeters cube, divided by the concentration of the concentrated solution, which is 12 molar. So this one is going to give me a volume equals to 41.666 periodic centimeters cube. Of course, we don't need so much accuracy here because the graduated cylinders that we use are not going to have so much. So the volume can be expressed as 41.7 centimeters cube, which is going to be 3 significant digits, the same as all the numbers that appear in the problem. In this problem, the wording is a little bit different, but the solution is exactly the same as the other one. It says, we calculated the concentration of potassium hydroxide solution using titration. That is extra information. And we obtained 0.150 molar. We still do not know if that is the concentrated or the diluted. So let's continue. 10 milliliters of this solution was placed in a volumetric flask. That means that was the volume that was extracted. That means that those 10 milliliters are from the 0.150 molar. And the volume at the end was 0.5 decimeters cube. Okay, so we need to do it the same as always. Volume 1, concentration 1, volume 2, concentration 2. Volume 1 is 10 milliliters. The concentration 1 is 0.150 molar. The volume 2 is 0.5 decimeters cube. And the concentration 2 is what we need to calculate. I would ask you to pause the video and think which is the problem here before going on. I'm going to wait like 5 seconds so you have time to pause the video and then I will continue. Okay, so the problem here, and maybe you didn't realize, is that we said that there is no issue with these formulas. They are super simple to resolve, and most of the time we don't have any problem. But in this particular case that we need to calculate the concentration, the second volume is given in a different unit than the first one. In the first one we have it in milliliters. In the second one we have it in decimeter cube, which is the same as liters, so it's not the same. So we need to pass this into centimeters cube. So I'm going to multiply by 1000 milliliters, which is the same as 1 liter. So liters can cancel, and this is 500 milliliters. And now I can apply my formula. So the concentration 2 is equals to volume 1, concentration 1 over volume 2. Volume 1 is 10 milliliters. The concentration 1 is 0.150 molar. And the second volume is 500 milliliters. So if we do the math here, the concentration 2 will be 3 times 10 to the negative 3 molar, and that must be expressed in, here we have one significant digit only, So we can express that like that. So, or 0.003 molar, which is the same thing. Okay? Most of high school students do not need these kind of questions like mixing the solutions of different concentration. But I decided to do it because it's very simple once you understand the concept, and maybe it helps you in the future. Okay, let's resolve this problem now. So we need to calculate the concentration of a solution after mixing. So the concentration is what we need to calculate. And the only information that we have is that we have 20 centimeters cube of a solution 0.1 molar. So 20 centimeters cube of a solution 0.1 molar of sodium chloride, and the other one is 30 centimeters cube of a solution 0.2 molar. The thing is that I take these two containers and I'm going to take those volumes that I had and I will fill out this other container. The question is, how can you calculate the concentration? We don't have number of moles, we don't have volume, but actually the volume is going to be the volume of the beaker 1. Let's say that beaker 1 and beaker 2. Okay, so in beaker 1 we have the volume, we put it together, so we are going to have in here 20 centimeters cube that comes from beaker 1 and 30 centimeters cube that comes from beaker 2. So the total volume, the volume is going to be 50 centimeters cube. Okay, now the other thing that I need to calculate the concentration is the number of moles. In this case we have sodium chloride, and sodium chloride it doesn't say that it's supposed to be sodium chloride as well. So I need to calculate how much would be the concentration. For that, I need to calculate first the number of moles here, and then the number of moles here. So in beaker 1, the number of moles is equal to the volume times the concentration, which is going to be, the volume is 20. Be careful, this has to be divided by 1000, so I have decimeters cube because or liters, because the volume has to be in liters, okay, times 0.1 molar. And in the beaker 2, the number of moles is going to be volume times concentration is equals to 30 centimeters cube. Again, I need to divide by 1000 times 0.2 molar. So the number of moles on the first one is 2 divided by 1000, which is going to be 2 times 10 to the negative 3. And in the other one is going to be 30 divided by 1000 times 0.2. That gives me 6 times 10 to the negative 3. So the total moles is equals to 2 times 10 to the negative 3 plus 6 times 10 to the negative 3. This one is going to give me 8 times 10 to the negative 3. Sorry, negative 3. And this is the number of moles of solute that are present here. So in the final beaker, we have in here, we have the volume equals to 50 centimeters cube, that is the addition of the two volumes, and the number of moles that we calculated separately, and then we added up 8 times 10 to the negative 3 moles. So the concentration is going to be 8 times 10 to the negative 3 divided by the volume. Be careful, the volume has to be in decimeters cube, so I'm going to put here 0.050 liters, and these are moles of sodium chloride. So it's 8 times 10 to the negative 3 divided by 0.050, 0.16 molar. Now, does it make sense? Well, this one is 0.1, which is the same as 0.10 molar, and this one is 0.2, which is 0.20 molar. I put a little bit, if I mix the same volumes of both of them, the concentration would be exactly 0.15. So 0.15 molar would be if they are exactly the same volumes. But in this case, because I put 10 centimeters cube more of the 0.2 molar, is going to be shifted a little bit towards the right. That means a little bit higher than 0.15, which is going to give me 0.16 molar. I hope that you enjoy the explanations. Please leave me your comments or concerns. And if you have any questions, you can address that in the comments as well. Thank you very much for watching.